Hello and welcome to Lecture 3 of Multiloop Circuits in PHYS 1204. I'm just going to close off the unit with some final words about energy transformations in circuits. A lot of this will be review of things we've seen in earlier units, but I thought it would be useful to collect it all together in one place. Let's start with the simplest of all circuits, a single battery and resistor, and the current runs around this way. And think of what happens in the battery. As we go from the negative terminal to the positive terminal, we know the potential is going up. Or to put it another way, we are moving against an electric field. And so charge moving in that direction has negative work done on it by the electric field. But remember, we can think of that as work done by the field due to some other charges, or we can think of it as a change in the electric potential energy of the whole system of charges. When the E field does negative work, the electric potential energy of the system is increasing. Well, that energy can't have come from nowhere. And what's going on, as we know, is that the battery is doing non-electrostatic work. We can quantify that as a work per unit charge, as an EMF, but ultimately what's happening here is that chemical energy is being converted into electric potential energy in the battery. Meanwhile, over in the resistor, the E field is pointing in the direction that the charges are moving because we're going from high potential to low. And so the E field is doing positive work. The system is losing electric potential energy here. And that is because charge carriers are colliding with atoms in the resistor. And so there's dissipation to thermal energy as those atoms now vibrate around. And so we're converting electric potential energy to thermal energy. One remaining complication is that conversion of chemical energy to other forms is never reversible, and so in fact the transformation going on in the battery must involve some production of thermal energy. If there's a significant resistance in the circuit other than the battery, then that production of thermal energy in the battery is negligible compared to the thermal energy production in the resistors. But if there isn't a significant resistance anywhere else in the circuit, then we can't ignore that, and there will be thermal energy production in the battery that is significant, or in other words, we can't treat the battery as ideal in a case like that. Overall, though, for any charge as it goes around the circuit, the amount of electric potential energy it gains in the battery is always equal to the amount of electric potential energy it loses in the resistor. And so there's no net production or consumption of potential energy. And so all that goes on in a circuit like this is that chemical energy in the battery is converted into thermal energy in the resistors. We can always think of a circuit as a system which includes the charges moving in the wires in the resistors and the chemicals in the battery. And wherever charges move through resistors, there's production of thermal energy, and wherever charge moves forward through a battery, there is a consumption of chemical energy. If charge moves backwards through a battery, then if the battery is rechargeable, chemical energy will be produced. But the main thing that happens when current runs backwards through a battery is just more production of thermal energy. All of this is true no matter how complicated the circuit of batteries and resistors is. You will always just have chemical energy converted into thermal energy. And since energy is conserved, the amount of chemical energy consumed must equal the amount of thermal energy produced. Or to put it another way, we can write it in terms of powers, so that we're now talking about the rates at which chemical energy is being consumed in the batteries, and that has to equal the rate at which thermal energy is being produced in the resistors. Now there are new possibilities when there is a capacitor in the circuit. We already know what's going on in the battery. Chemical energy is being converted into electric potential energy and thermal energy. What's going on in the capacitor is that we are storing that electric potential energy. One way to think of it is that as the capacitor is charging, charges are being moved against an electric field through the wires until eventually that electric field disappears. But in any case, we're doing work against an electric field the whole way, and so we're storing electric potential energy. But probably the easier way to think about it is just that we are storing electric potential energy in the electric field in the capacitor. And so as that electric field gets stronger, we're storing more electric potential energy. And so overall, in this circuit, what is going on is that chemical energy is being converted into electric potential energy in the capacitor and thermal energy in the battery. And we can always, in defining a system, include the E fields inside the capacitors. And when those E fields get stronger, the circuit is producing electric potential energy that is stored. In this case, we know how to calculate just how much energy is transformed into every form. We know that eventually, once the current stops flowing and there's no potential difference across the resistor, that the EMF of the battery is equal to the potential difference across the capacitor. At that point, some charge, Q, has been pulled off one plate of the capacitor and moved around onto the other, passing through the battery in the process. And so now we have some plus Q on one plate and negative Q on the other plate, and during that process, the battery has done work to pull a total amount of charge Q through an EMF epsilon. Meanwhile, we know that the amount of potential energy stored on the capacitor is a half the charge times the potential difference, and that potential difference is the same as the battery's EMF. But notice that that means only half of the chemical energy that was consumed in the battery ended up as potential energy in the capacitor. All the rest ended up as thermal energy, and whether there's another resistor other than the battery's internal resistance or not, the total amount of thermal energy produced is the same. If we flick the switch in the other direction, now the capacitor discharges through this other resistor, and all of the electric potential energy stored in the capacitor will be converted into thermal energy in the resistor. Finally, let's think again about inductors. So if we have just flicked the switch over to A and there was no current running before, then there would be no current running initially at the moment that the switch is flicked over to A. But now the current will gradually increase, with the inductor resisting that increase, but it has to lose out in the end, and that current has to eventually reach some higher value. During that process, early on, chemical energy in the battery is being converted into magnetic potential energy in the inductor because the B field in the inductor is getting stronger, and we know that fields in a volume of space store potential energy, and simultaneously thermal energy is again being dissipated in the internal resistance of the battery. That only happens early on as the current is increasing. Eventually the current will be as big as it's ever going to get, and from that point on, there is no more change in the potential energy in the inductor, and all that's happening is that chemical energy is being converted into thermal energy. Now if we flick the switch over to B, though, all of the energy that was stored as potential energy in the inductor has to eventually get dissipated to thermal energy in the resistor. Overall, what's going on here is that in addition to the forms we've talked about before, we can also think of the system as including the magnetic fields inside inductors, and when those fields get stronger, the system is producing magnetic potential energy. There's one more important and interesting case for us to look at, and it's the case of what is called an LC circuit, a circuit containing an inductor and a capacitor. And so let's suppose we have previously charged the capacitor, probably with a battery, and we've now disconnected that battery. And now we close this switch. With the switch closed, current is going to start flowing as the capacitor discharges. However, note, we already know that just after the switch is closed, the current through the inductor must be the same as it was before we closed the switch. And so if we call t equals 0 the time when we close the switch, the current must be 0 at that time because there was no current flowing before we closed the switch. What's going to happen now will be a little bit like what happened when we discharged a capacitor through a resistor in an RC circuit. But we're going to see that something rather different happens because an inductor behaves nothing like a resistor. As usual, let's write a loop law. So I'm going to do the loop around this way, and in particular, that is because I know there is then a potential rise as I go through the capacitor, and so there must be a potential drop as I go through the inductor. Because I know there is a potential drop as I go through the inductor, this is a drop, and so di by dt must be positive. In other words, the current is increasing, which is not surprising since it started at 0, and we certainly expect the capacitor to discharge. Now note that both the current and the charge on the plates are functions of time. And in particular, the current is telling us about the rate at which the charge on the plates is decreasing, or in other words, the current is negative dq by dt. With that realization, we can rewrite our loop law all in terms of q, because di by dt must therefore be the negative second derivative of the charge. Well, that's a differential equation, but it's a rather easy one, because this is saying that q is a function of time such that when we take its second derivative, we get the same function back, but with a negative constant out front. Well, again, we know what kind of function does that. For example, the second derivative of a cosine does exactly that. And so q must be a sinusoidal function, and cosine will fit the bill because we know that it started off non-zero, and so we want a sinusoidal function that starts off non-zero. And so now, looking at this, we can simply see that the angular frequency omega must be 1 over the square root of LC. And that, then, is our answer. Q as a function of t is q naught cosine of an angular frequency times t, with that angular frequency determined by the inductance and capacitance of the circuit. Notice then what's going on in this circuit in terms of energy again. At the beginning, the circuit has a lot of electric potential energy, but after we close the switch, an oscillation occurs where electric potential energy in the form of charge stored on the capacitor, or alternatively electric field between the capacitor plates, is converted into magnetic potential energy in the inductor, and then is converted back, and it goes back and forth from one form of potential energy to the other, with no dissipation. The total lack of dissipation tells you that for any real circuit, this doesn't really happen. In particular, an inductor is a long, usually rather thin wire, and so there must be some resistance in the circuit. And so, in fact, instead of simply seeing an oscillation of the charge on the plates as a function of time, we would in practice see a damped oscillation.